And now we're going to take a look at mass spectrometry. This is in chapter 14 of Klein, and so you can refer back to it for that. With mass spectrometry, we're looking at the mass of various substances. In short, a sample is placed into an ionizer. There are various different types for various applications. The ions that are formed are sent through a magnetic field, which will separate them based on their mass, and then those ions will hit a detector and be recorded as a signal. That's what we read out. What happens to the molecules as they are sent through the mass spectrometer is they encounter some high energy source, whether that be a very high electric field, a large potential difference. It could be a beam of electrons blasting them. Whatever that energy source may be, it turns it into what's called the molecular ion, which is everything in your molecule is the same except we've blasted away one electron. As a result, we're left with a positively charged molecule that has lost its electron. And because of the instability of this, these experiments are often conducted in a vacuum so that there's nothing to react with our molecular ion, because it would react, right, to try and get its electron back. And so what we detect here is what's called the mass-to-charge ratio, which is labeled as m/z, where mass and charge would be m and z respectively. Most molecular ions have a charge of 1, so the molecular ions that we see there would be the same mass of the molecule that we put in. And as we know, the mass of a substance can give us a very good, a lot of information about its chemical formula, right? As well as its structure, as we'll see with fragmentation patterns. Because the molecular ion is unstable, it frequently will fragment into smaller pieces. And so by piecing together these fragments, that gives us structural information about the molecule, just like how NMR did in last semester. We're going to take a look at some mass spectra here in just a second. But first I want to do some terminology. One thing that we want to note is that we have something called the base peak, which will be our highest abundance within the spectrum. That's not necessarily the molecular ion. The molecular ion itself is our original molecule just minus one electron. And so it will have the same mass as our original molecule. And so these two do not need to be the same, as we will see with the mass spectrum of pentane. So let's take a look at that and see what we can figure out. So here it is, our mass spectrum of pentane. I'm going to just move this over a little bit. As we can see, our y-axis there is relative abundance or intensity, and our x-axis is that mass-to-charge ratio. I'm going to just move this over so we can see all our peaks. Pentane has a molecular mass of 72 grams per mole. And we do see that way over here on the right. We see 72. That would be our molecular ion peak. That should be the largest peak at the highest molecular weight that you see. You will see smaller what are called satellite peaks as a result of isotope effects. For example, carbon-13 would give you that 73 by having one carbon that has one extra neutron. 71 we might see if we've blasted off a hydrogen as well. So you'll often see kind of very important peaks and then peaks with a few, small little tweaks here and there. In this peak, our base peak is 43, which corresponds with 3 carbons as well as their hydrogens. And so that tells us that this pentane is fragmented into a component that has 3 carbons and one that has 2 carbons. And we see those 2 carbon fragments down here, depending on their number of hydrogens. And so we put those together, and lo and behold, we've got our 72 again. So this is what we're looking at here. Our first step is to identify the molecular ion peak, which should be your highest one that is of significant intensity. So we're going to go ahead and say that one is 72 for pentane, and it should be because pentane's molecular weight is 72 grams per mole. All right, In the next video, we'll take a look at some isotope effects and see how we can identify the number of carbons, chlorines, bromines, or nitrogens from a mass spectrum. And then after that, we'll take a look at fragmentation patterns, so we can see some structural information about the location of functional groups within the molecule.